Here we have graphs of two functions, f of x, and actually it's not the graph of the functions, it's the graph of the derivative of the function, so you have to be very careful. Sometimes you may be given the graph of the function itself, or sometimes you may be given the graph of the derivative. Now when you're given the graph of the derivative, it's better if you change it to the number line. So it's hard to see here, but this is 3 and this is 0. So if you put 0 and 3 on the number line, and this is y f prime, so when the graph is above the x-axis f prime, that means it's positive, right? If the graph is above the x-axis, it's positive, and if the graph is below the x-axis, it means negative, right? And these are the values of f prime because this is the graph of f prime. Now, what does that mean for the function f? It's decreasing and increasing and increasing. So we know that for f, critical numbers are 0 and 3, whereas 0 is a relative minimum, whereas 3 is neither relative minimum or maximum. Okay, here this is -1 and this is 2 and 0. Okay. Oh, by the way, we also have to do the inflection points. Okay, so for inflection points, see, the graph is increasing up till this point, and that's equal to 1, and decreasing between 1 to 3, and after 3 it's increasing. So the slope of f prime is positive until 1, and negative between 1 and 3, and then afterwards it's positive. Okay, and because the slope of f prime is the derivative of f prime, what is the derivative of f prime? It's f double prime, right? So that's why this is plus minus plus, and you can see that there's a change in concavity before and after 1 and 3. Therefore, you can say that 1 and 3 are inflection points. Okay, that's what we know for f. Now let's go to g. G, again, g is 0. G prime is 0 at -1 and at 2. And you can see that the graph falls below the x-axis between -1 and 2, and also after 2. So it's minus and minus, and before it's plus. And this is talking about g prime because the graph is g prime. Now what about the slope? It's decreasing up till 0, and then increasing up till 2, and decreasing afterwards, right? So it's up till 0, it's decreasing, and afterwards it's increasing, and after 2 it's decreasing again, and this is the slope of g prime, which is g double prime. Okay, all right. This tells us that for g it's increasing, decreasing, and then decreasing. So we know that the critical numbers of g are -1 and 2, whereas this one is relative max, but 2 is neither. Okay, and also from here we see that 0 and 2 are inflection points. Okay, now let's go to the next question, 38. Okay, suppose you're given a function whose derivatives are the following. Okay, let's also say that it has a vertical asymptote at x equals to -3. You can see that x equal to -3 makes the denominator 0, so it's kind of reasonable to think that there must be a vertical asymptote, but it doesn't have to be. Determine the intervals on which f of x increases, decreases, the interval on which the function is concave up, down, and the x values in which the function has maximum, minimum, and inflection. Okay, all right. So first, in order to figure out where it's increasing or decreasing, you need to know the sign of f prime. And to find the sign of f prime, you need to put the number line and put the critical numbers. As you can see here, f prime of x is 0 when x is 1 or equals to 6. Also, at x equals to -3, it's undefined. So x equals to -3 is not a critical number, but it's still a possible place where the sign change could occur. So even if this is not a critical number, you should still put in here. Okay. Now let's plug in a few values. So we'll pick test values, say -4, 0, and then 2, and then 7, 4 into this f prime to see what the sign of f prime is. Okay, if I plug in -4, this is negative, that's negative, the bottom is negative. So you have negative times negative divided by negative, which is negative. If you plug in 0, these are negative, but the bottom is positive. So you have negative times negative divided by positive, so it's positive. If you plug in 2, negative times positive over positive, so it's negative. And if you plug in 7, everything is positive, so you know that it's positive. Okay. All right, what about f double prime? We can do the same exact thing for f double prime. For f double prime, you have -9 here, and you have -3 here, and then +3. Okay. So -9 and 3 are those places where f double prime is equal to 0, and -3 is when the denominator is equal to 0. And these are the places where possible sign change could occur. Okay, so let's try that. This is f double prime. Let's pick a point, -10. Another test point, -4, 0, and then 4. Let's plug that into this function. -10 is negative, negative. The bottom is squared, so it's always positive. So when you have a square in the denominator, then just don't worry about it. Just think about what the sign of the top is. So it's negative times negative, it's positive. And if you plug in -4, it's positive times negative, so it's negative. If you plug in 0, it's still positive times negative, it's negative. And if you plug in 4, it's both of them are positive, because 4 plus 9 is 13, 4 minus 3 is 1. So this is positive. Okay, using these information, we can now say that the function is increasing between -3 and 1, and also after 6. Okay, so let's try to talk about increasing interval, increasing from -3 to 1, and then after 6 to infinity, it's going to increase. How about decreasing? That's the from -infinity to -3, union 1 to 6. And then concave up is when you have positive second derivative, so it's between -infinity till -9, or 3 and afterwards, right? Concave down is when you have negative second derivative, and that's -9 to -3, union -3 to 3. Notice that I intentionally split off at -3, because at -3 the function is undefined, and therefore you can't talk about concavity at -3. So you really need to put these two intervals. Okay, now let's talk about the maximum minimum. Since the function is decreasing and then increasing and decreasing and then increasing, we know that at -3 and 6 you have a relative minimum. So relative minimum at x equals to -3 and 6, and relative maximum at oh, actually, sorry, this is not good, because at -3 you have to be careful. The function is not defined. It's not one of the critical numbers. That's why it's important to know that -3 is not a critical number, so that shouldn't be there. And relative max, we see here that at 1 it's going up and then down, so it's x equal to 1 is relative max. Okay, for the inflection points, let's again be careful not to include -3. there is definitely a change in concavity before and after negative 9 and 3. So inflection points at x equal to negative 9 and then 3. Sketch a graph satisfying the following conditions. Okay. Yeah. It's always handy to see if you can put some number line. So I guess these are not inequalities. I don't know if anything is positive or negative, so you can't change this to number line. But this one definitely can put into number line. F double prime. Let's put this in there. There is a sign change before and after negative 1, and also at 1. Okay, and it says between negative 1 and 1, F double prime is negative, whereas for the other cases, F double prime is positive. Okay, so that tells us that there's a change in concavity, so negative 1 and 1 are inflection. Okay, and then let's see, F prime is 0 at negative 2 and 0 and also at 2. Okay, now although it's hard to see whether f prime is positive or negative, this kind of gives you some clue. The value of f gives you some clue. So at negative 2, the value of f is negative 1, and at 0, the value of f is 1, and at 2, the value of f is negative 1 again. So from here to there, it must be increasing, right? And from here to there, it must be decreasing. Okay. Another thing that you can notice is that at negative 2, f double prime is positive. So what does the second derivative test say? It must be relative minimum. Same thing for 2. F double prime is positive. Second derivative says that 2 will be a relative minimum. So that forces us to say that it must be going up like that, and going down like that. So using this, we can kind of see that f prime must be negative before, positive between, negative after, positive. Okay. All right. So since we've completed these, now we are ready to draw the graph. Let's try to draw the graph. Here, negative 1 and 1, negative 2 and 2, 1, negative 1. At negative 2, the function is negative 1. At 0, the function is 1. At 2, the function value is negative 1. So we need a graph that passes through these 3 points. And because of the concavity from here to negative 1 and before, it has to be concave up. Between negative 1 and 1, it has to be concave down. And after 1, it has to be concave up. Okay, so that's the graph needed for part A. Now let's go to part B. We already said it, but since f double prime of 2 is positive and f prime of 2 is 0, the second derivative test says x equals to 2 is a relative min. Okay, and same for x equals to negative 2. Okay, so if, same can be said of x equals to negative 2. It must be a relative minimum. Okay. And part C, find the inflection points and the intervals on which the graph is concave up or down. Well, this already tells us what to do. It's concave up on negative infinity to negative 1, and also 1 through infinity, and it's concave down between negative 1 and 1. Okay, fill in the table and use the table to graph y equals to f of x. Okay, let me make this larger because I need to have some place to write. Okay, first the graph passes through -1, -4/3, so it's -1, -4/3, and also 0, 0. Okay, f prime of x is less than 0. What does that mean? The graph is decreasing. F prime positive means it's increasing. F double prime negative means it's concave down. F double prime positive means it's concave up. This again means concave down. And then this limit means y equals to 3 is a horizontal asymptote. And then this limit means y equal to 0 is also a horizontal asymptote. And so y equal to 0 will be the horizontal asymptote, the place where the graph gets closer and closer to as x goes to the left. And as x goes to the right, the graph has to be closer and closer to y equals to 3. Now, let's try to draw the graph using the information that we have. So we know that the graph must pass 0, 0, and also -1, -4/3. So it has to pass through these 2 points. Okay, and before -1, the graph must be decreasing, so it must be decreasing, and then increasing up till, it should be increasing continually, okay? There is, however, a change in concavity. Before -2, there's a change in concavity. It should be like this at -2, okay? And then after 0, the concavity also changes. It has to be like that, okay? And then finally, for the asymptote to the right to be 3, it should be 3 going that way. And for asymptote to be 0 on this way, that means this portion should be much lower. So let me slightly change this. This portion should be lower. It's still concave up until -2, but then the concavity changes and it goes like that, and the x-axis itself is a horizontal asymptote where the graph gets closer and closer. Y equals to 3 is also the horizontal asymptote as the graph goes to the right. So that's the graph. Now in this graph, you see that this point here is a relative minimum, and also the absolute minimum, right? This is saying it's absolute minimum is not required by the problem, but it's good to know. And also at 0, 0, you have an inflection, and also here you have an inflection. The graph of fx is shown below. Okay, first question, what is the domain of this function? You can see that the graph stops at -4. There's no graph before -4, and also it stops at 7. There's nothing after 7. So we know that the graph has the domain from -4 to 7. The only thing that you also have to consider here is what happens at 1. If these were both open circles, then the value of 1 will be undefined, but f of 1 is 0 according to this graph, so it is defined. So we know that the domain is just everything from -4 to 7. What are the critical numbers? What's a critical number? Those are the points where you have the derivative equal to 0 or derivative does not exist, and it has to be in the interior point of the interval. So -4 and 7 you don't consider as critical numbers, but see here there's a horizontal tangent, so f prime is 0 here. And also there's a jump discontinuity. If it's not continuous, we know that it's not differentiable. So this point will be the place where f prime does not exist. Okay. And for that reason, we know that critical numbers are x equals to -1 and 1. C. Is f double prime -2 positive, negative, or 0? So let's go to -2. We're looking at this portion. Is this concave up or down? It's like something is pushing from below, so it's concave down. If it's concave down, f double prime is less than 0. So f double prime of -2 is less than 0. Now what about this one? At 4, you have a portion of the graph which is a straight line. If it's a straight line, it's neither concave up or concave down because it's not being pushed in any direction, neither from above or from below. It's not being pushed. So in that case, f double prime will be equal to 0. Okay. What are the x coordinates of absolute maximum and absolute minimum? Okay. Absolute max and absolute minimum are places that are highest on the graph and the lowest in the graph. I think the highest point on the graph is right here, which also happens to be the relative maximum. So at x equals to -1, you have absolute max, and at x equals to, let's look for the lowest point. See, this is the lowest point, so at x equals to -4, you have absolute minimum. Okay. And then E, oh sorry, this is E and this is D. And then F, find the interval where f prime is less than 0. F prime being less than 0 is when it's decreasing, right? But because f prime is not defined here, we can't include 1. So f prime is less than 0 between -1 and 1 because it's decreasing there. And union, after 1 until 7, it's also decreasing, so the derivative must be negative there. Is this function continuous at x equal to 0? Explain. Okay, here we have a piecewise function. Let's think about the limit of x going to 0 minus of f of x. Well, because when x is negative, it follows this definition here. So we should really be plugging in 0 into the second function, 1 minus 0. So the limit from the left from 0 is 3. Now let's look at the limit from the right. In that case, it follows the top one. So when we plug in 0 to the top function, we end up with 0 over 1, which is a 0. Now, do these agree? Do not agree. What does that mean? That means that limit of x going to 0 of f of x does not exist. And if you recall, continuity of a function means first the limit has to exist and the value of the limit has to be equal to the function value at that point. So if the limit doesn't exist, that automatically means that it's not continuous. So A is not continuous because limit does not exist. Okay, there are other reasons where you may not have continuity, but the reason for this one is it's not continuous because the limit does not exist. Okay, now let's find all critical numbers. Okay. If you differentiate each function, let me get help of some mathematical software to differentiate. So let me see, differentiating 3x squared plus 4x divided by x squared plus 1. X gives you gives you the following. So this actually, if you have to do it in the actual exam, it will take a while. But after, for differentiating and factoring, you'll see that the top function can be factored in this format. Maybe I should, instead of writing it negative 2 plus x, let me write it backwards. Negative 2 times x minus 2 and 2x plus 1. This is what you're going to get if you differentiate the top one when x is positive. And for the bottom one, you're going to get 3 over 1 minus x squared for x less than 0. Now, one thing that you have to be careful is that this is valid only for x strictly less than 0, because we already know that f is not continuous at x equal to 0. Since it's not continuous, f prime cannot exist at x equal to 0. So it would be wrong to include 0 for this one. Okay? So these are the derivatives. Now, when is this one equal to 0? It's equal to 0 at x equals to 2 or negative 1/2, because it's only, this formula is only valid for positive x. The negatives do not work, and x equals to 2 is the critical number because it makes the f prime equal to 0. For this one down here, differentiate, putting the numerator equal to 0, you see that that never happens. The numerator is always 3, so it can never be 0. So this is never 0. So only time when f prime is equal to 0 is when x equals to 2. So what are the critical numbers? Critical numbers are it's x equals to 2, and the other one is x equal to 0, because we already know that at there f prime does not exist. Okay, now let's try to figure out whether these are relative max, relative min, or neither. Okay, so let's put the critical numbers 0 and 2, and f prime. If I plug in anything negative, it goes into here, and this is positive divided by positive, so f prime is always positive before 0. Between 0 and 2, if I plug in, say, 1 as a test value, this is positive, that's positive, this is positive, negative 2 is negative, so you end up with a negative here. Okay. Oh, sorry. 1 minus 2 is negative, so you end up with a positive here. Okay. And then for 2, you have after 2, if I put 3, 3 minus 2 is positive. This is positive, 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 but negative 2 is negative, so you end up with a minus here. So what do we have? We see that the function is increasing. Function is increasing, and then increasing again, and then decreasing. Okay. However, you have to be a little careful when you have a non-continuous function. See, we know that it goes up till 3, so the value is 3, but suddenly jumps down to 0 because the right limit is 0, and then goes up again and then comes down. So if you try to imagine what the graph looks like, it goes up, suddenly goes down, and goes up again and comes down. Now in this case, would you consider this part as a relative max or relative min, or neither? Well, if you only take this portion of the graph, isn't this the highest inside this small neighborhood? So we know that this is a relative maximum, even though f prime is positive and positive. So you have to be careful when there is a jump discontinuity, because when that happens, then even if f prime is positive and then positive, you could still have a relative max, or vice versa. You may have relative min, depending on which one it is attached to. Okay, so this is relative max. And again, this point is relative max. Okay, so both are relative maximum functions. Okay, find all asymptotes of this function. All right, first of all, the top one doesn't have any asymptote because the denominator is never 0. See, x squared is always positive. Positive plus positive is positive, right? X could be 0, but this denominator is 1 or greater, so it's never 0. This denominator can be 0 when x is equal to 1. However, we are limiting in this case to x lesser equal to 1. So this x equals to 1, the vertical asymptote, is not shown because we're limiting its domain up till here. Therefore, there's no vertical asymptote. So here, no vertical asymptote. Okay. However, we need to come up with the horizontal asymptote. Let's see. So in order to do the horizontal asymptote, we should do the limits. Okay, so let me compute the limits where x is going to positive infinity and negative infinity. So let's compute limit x going to positive infinity of 3x squared plus 4x over x squared plus 1. Well, they are both x squared, so we know what the limit must be. It should be 3, right? What about limit x going to negative infinity, 3 over 1 minus x? See, for this one, I have to use this one because if x is negative, I have to use the second function, right? In that case, it's 3 over 1 minus negative infinity, and that's 3 over infinity, which is 0, because if you divide 3 by an infinitely large number, it gets smaller and smaller, close to 0. Therefore, these two shows us that the horizontal asymptotes are y equals to 3 and y equal to 0. Those are the part E. Okay, find the horizontal asymptotes of each function. So part A, we already discussed that if you have an absolute value function, you can rewrite it as x minus 1 and negative of that thing, depending on whether the inside is positive or negative. Okay. If x is less than 1, then x minus 1 becomes negative. Therefore, in order to make it positive, you need to put a minus in front. So don't be fooled by this negative sign here. This is a positive value. Okay. Therefore, if you divide it by 3x plus 2, what would you get? You'll be just dividing by 3x plus 2 both cases, right? Therefore, when you take limit x going to positive infinity of absolute value of x minus 1, 3x plus 2, that's same as taking this part limit, x going to infinity, of x minus 1 over 3x plus 2, and therefore you get x over 3x, which is 1 over 3. For the other direction, x going to negative infinity, the function is now the second one, so we replace it, plus 2, and then, sorry, it's a mistake here. X goes to negative infinity, negative x minus 1 over 3x plus 2. In this case, negative x over 3x gives you negative 1/3. And therefore, we know that the horizontal asymptotes are y equals to 1/3 and y equals to negative 1/3. Let's approach the second one. Now, for second one, this might look familiar. You probably have heard many times that if you're taking the limit of something with 1 minus cosine, you should multiply the conjugate. However, this is that rule doesn't apply here because, as you can see, the denominator is infinity squared, and cosine x is a number that's between negative 1 and 1. So it can never, this numerator can never be bigger than 2 or less than 0. So it's just some finite number on top, whereas the denominator is very large. So this limit will be 0. Okay, that also happens for limit x going to negative infinity. So in both cases, we know that the horizontal asymptote is y equal to 0. Okay, find each limit if it exists. All right, A, limit x going to infinity of x times sine of 1 over x. The thing is, if you naively plug in infinity, 1 over infinity is 0, so you get sine of 0. What is that? Sine of 0 is 0. So this much gets closer and closer to 0, very small. But at the same time, this one goes to infinity. It's really, really large. So if you have something that's growing ever larger and larger, times something that's going ever slower and slower, what would be the limit? Well, you really can't tell, because it really depends on which is growing faster. So if x is growing much faster to infinity than sine 1 over x going to 0, then this will be a huge number, or it might even diverge. But if it's the other case where sine 1 over x goes to 0 much faster than x, then the limit could be 0. So we talked about that 0 over 0 type and infinity over infinity types are indeterminates, meaning that you really need to work harder to figure out the exact value. You can't just look at this and say the limit is 0 or 1 or anything. And in this list, you should add this one, that infinity times 0 is also an indeterminate. Okay, so these are indeterminate forms. Okay. Now, the proper way to solve this is to do a substitution. So say t is equal to 1 over x, so you get sine of t. Now, if t is equals 1 over x, what does that mean for x? What is x? I can multiply x both sides to get x times t equals to 1, and that means x is equal to 1 over t. And that's important because I need to know how to replace this x. Now I know that x is 1 over t. I can replace it like that. And then if x goes to infinity, where does t go? So as x goes to infinity, we know that t goes to 1 divided by infinity is 0, right? So that means I can rewrite this limit here as limit t going to 0 of 1 over t times sine of t. Now this may look familiar already, but if it's not familiar to you, then think about the fact that 1 over t times sine t is same as sine t over t. What's this limit? That's just 1. Okay. Now let's think about part B. Let's use a different color. B, limit x going to infinity of e to the 1 over 1 minus x. Well, what is 1 minus infinity? X is infinity, so 1 minus infinity is negative infinity, right? But if you divide 1 by a very large negative value, that's still 0. So you get e to the 0th power, which is 1. Okay, so that was really simple. Let's go to part C. Limit x going to 2 plus of 5 to 3 of 4 minus 2x. Okay. Now, we see that 4 minus 2x can be factored like 2 times 2 minus x. All right, and then if you plug in 2 plus here, so you subtract from 2 something slightly larger than 2. 2 plus means it's slightly larger than 2. So you get a 0 minus. Right? So you end up with 5 to 3 over 2 times 0 minus, which means you have a negative in the denominator, positive on the top, so overall this is negative. and because the bottom is getting closer and closer to 0, overall it has to be going to infinity. So it should be negative infinity. So we have 5 to the negative infinity. What is that? That's 1 over 5 to the infinity, because negative power means 1 over. And you're dividing 1 by a very, very large number, so you get 0. So the answer to part C is 0. Let's continue with D and E. D, you have limit x going to infinity. This is like 0x squared plus 5x over x squared plus 7, right? If you put x squared, because that's the highest term in the denominator, and view it like this, it's the limit is just 0 over 1 times x squared. So it's 0 over 1, which is just 0. Okay. For E, limit x going to infinity of ln of 2x minus ln of 3x minus 1. Recall that there's a rule for logs where if you subtract 2 logs, that can be put as a single log, and the minus turns into division inside the log. So subtraction between 2 different logs can be written as division inside a single log. So you have 2x on the top and 3x minus 1. Now you know where this goes. It basically goes to 2x over 3x, which is 2/3. So the limit in this case is like ln. It's similar to 2x and 3x. So that's just ln of 2/3. Find the absolute extrema of the function in the given interval. Let's find the derivative. F prime is 2/3 comes down, and you have to subtract 1 from 2/3, is negative 1/3, and negative 3 is just a constant, so it's equal to 0. So we have this, which is 8/3 of x to the negative 1/3, and because minus means 1 over, so it's really 8 over 3 times x to the 1/3 power. Okay, so when is this equal to 0? Never, because the numerator is never equal to 0. When does the derivative not exist? Well, if the denominator is equal to 0, then f prime does not exist. So we know that at x equal to 0, f prime does not exist, and therefore x equal to 0 is a critical number. And that's the only critical number that we found. Once you have the critical numbers and also the boundaries, to find the absolute extrema, you just have to evaluate the function at the boundaries and the critical numbers and just compare from inside, from those, right? So f of 0 into the original, it's 4 times 0 to 2/3 power minus 3, so that's just negative 3. How about f of negative 1? Okay, 4 times f of negative 1 is like negative 1 squared and 1/3 power minus 3, and negative 1 squared is 1. Anything squared is positive, so this is positive 1. 1 to the 1/3 power, 1 to any power is 1. So you get 4 times 1 minus 3, which is 1. Okay. How about f of 64? Well, in order to compute this easily, recall that 64 is 4 to the 3rd power. So when you take the power of 2/3, 3 cancels, and you get 4 squared, which is 16. 16 times 4 is 64, so you have 64 minus 3, which is 61. Okay. Among these values, I see that this is the max, the highest between this and this, right? And this one is the minimum. So we can say that the absolute max is 64, 61, and absolute min is 0, -3. Okay, for part B, f prime of x equals to 3 cosine of x. And if you set the derivative equal to 0 in this domain, let's see, what's the graph of the cosine? Cosine graph is like 2 pi, pi, and then it's like this, right? So if you take the portion of the graph from pi over 45 degrees up till here, it's 2/3 pi. 2/3 pi is less than pi, right? Actually, 2/3 pi is 120 degrees, so it's before 180 degrees. So it's this portion. And you can see that the only place that the cosine is equal to 0 is when x is equal to, when x is equals to pi over 2. That's the only critical number. Okay, now all we have to do is evaluate the function at the critical number and also at the boundaries. F of pi over 2, what's 3 of sine pi over 2? Sine pi over 2 is 1, so that gives you 3 times 1, which is 3. And then f at one boundary point, pi over 4, gives you 3 times sine of pi over 4 is right equal to 2 over 2. And f of 2 pi over 3, sine value is positive right equal 3 over 2. And let's see, this is 6 over 2, so, and this is 3 times 2, right? So we have basically 3 times 2, 3 times right equal 2, 3 times right equal 3. So let me rewrite this, 3 times 2 over 2. So if you look at just 2, right equal 3, and right equal 2, we know that this is the smallest and this is the largest. Therefore, the answer is absolute max is pi over 2, comma 3, and absolute min is the smallest is pi over 4. Pi over 4, comma 3 right equal 2 over 2. Okay, now let's move on to part C. Part C, you have f prime of x. It's a product of two functions, 4x squared and this exponential function. So you need to use the product rule. 4x squared prime e to negative x squared over 4 plus 4x squared e to negative x squared over 4 prime. Okay, 4x squared differentiates to 8x. And this one you need to use the chain rule because negative x squared over 4 is nested inside. So the derivative of this function comes outside, which is negative 2x over 4. And e is the negative x squared over 4. And as you can see, this 4 and that 4 cancels away. And then you end up with negative 2x cubed. And since these two terms have e to the negative x squared over 4 as a common factor, let's factor that out and see what we get. We have 8x from the first term, and the second one is negative 2x cubed. Now even this, you can factor a 2x out. So let's do that. 2x e to the negative x squared over 4. And that gives you 4 minus x squared. Okay. Now when is this equal to 0? Either when 2x is equal to 0 or 4 minus x squared is equal to 0. This is 0 when x is equal to 0. 4 minus x is equal to 0 when x squared is equal to 4. That's when x is plus minus 2. But then you have 0, 4 as the given interval, and boundary values are never considered as critical numbers. So x equal to 0 is not considered as a critical number. x equals to negative 2 lies outside the domain, so therefore the only critical number is x equals to 2, is the only critical number. Okay. Now let's continue on. Now evaluate the function at 0, because that's the boundary, but that's just 4 times 0 squared times e to something, it's 0, so 0 times anything is 0, so that's 0. What's f of 2? F of 2 is 4 times 2 squared e to negative 2 squared over 4. That's 2 squared is 4, 4 times 4 is 16. 16 times e to the 4 over 4 is 1, so it's e to the negative 1, which is 16 over e. And f of 4 is 4 squared is 16 times 4 is 64. 4 squared is 16 minus 4, so it's 64 divided by e to the 4th power. Okay. Now these are both positive, so we definitely know that the 0 is the smallest one, so we know the absolute minimum is 0, 0. But then we still need to figure out which one's bigger. Well, the top one, from 16 to 64, is multiplied by 4 times. However, e is about 2.7, so 2.7 is divided 3 more times down here. So you're dividing by e 3 more times, so that makes this smaller. Okay, so you can say that the absolute maximum, the highest value, is when x is equal to 2. Okay. All right. Now for part D, just factor this. How does this factor? This factors as x minus okay. This one, I thought you could factor this, but you can't. Right, actually, sorry about this. I made the numbers very messy. If you found the 0 of this one, you will see, using the quadratic formula, you'll see that the 0 of this is 1 plus minus square root of 13. Okay, are the zeros. And because square root of 13 is 3 point something, 1 minus square root of 13 is less than negative 2. So 1 minus square root of 13 is outside the domain, and therefore the only thing that lies inside is 1 plus radical 13. That's the only thing between negative 1 and 5. So here's what's happening. Here's 1 plus square root of 13, and there's 1 minus square root of 13. And without this absolute value, this is a graph that's a parabola, right? It's a parabola. However, because of this absolute value, anything that falls below the x-axis gets flipped over like this. So that's the graph, okay? And we also know that if you take the midpoint of 2 zeros, that's when you have the vertex, right? And because this is 1 plus radical 13 and this is 1 minus radical 13, the midpoint is exactly 1. So at 1, you have the vertex. So that's it. What are the critical numbers? The critical numbers are 1 and 1 plus radical 13. And then we definitely know that 1 plus radical 13, if you plug that, it's 0 because it touches here. So this is 1 plus radical 13 comma 0. That's the absolute minimum. Okay. Now for the highest point, it's either this point or that point, but judging from the graph, it's probably 5. Okay. So let's just do a quick estimation. 1, if you plug in 1, 1 minus 2 is negative 1, negative 1 minus 12 is negative 13. So positive 13 is what you get. That's the value at here. If you plug in 5, 5 squared is 25, minus 10, so it's 15. 15 minus 12 is 3. Oh, okay. So I thought, I guess the graph is not so close to scale, so I thought it'd be much higher, but at 5 it's 3. So the maximum is, absolute maximum is at 1, 13. Find all critical numbers of this function. F prime of x is 4 radical 3 cosine of x minus 6. Now let's set it equal to 0 because we are looking for critical numbers. So 4 radical 3 cosine of x is 6. Divide, and you get 6 divided by 4 radical 3, and because you have a radical in the denominator, you should multiply radical 3 top and bottom, which is 12 in the bottom, because radical 3 times radical 3 is 3, 3 times 4 is 12, and 6 radical 3, 6 over 12, that's 1/2, so radical 3 over 2. Okay. So that is the value, the critical number. That's actually, oh no, it's not the critical number yet. I almost got fooled, sorry. Cosine x has to be radical 3 over 2. That's when you have the critical number. So let's draw the graph of the cosine. Cosine 1. It's like this. And it's a high value, so it's 1 is here, another is here. So the actual value where cosine x is equal to radical 3 over 2 is 1 is at pi over 6, or the 30 degree one. The other is in 330 degrees, or in terms of radians, it's 11 pi over 6. Those are the places where you have the critical numbers. Okay. Now, for each of the critical numbers, we have to use the second derivative test. If we don't use the second derivative test, the problem says we can't get any credit. So let's use the second derivative. I have to differentiate this one more time. Cosine difference is negative, so it's negative 4 radical 3 sine of x. Negative 6 differentiates to 0 because it's a constant. Now let's evaluate at each point. F double prime at pi over 6 is negative 4 radical 3 times sine pi over 6. Sine pi over 6 is 1/2. So that's negative 2 radical 3. So it's negative, okay? So we have a frowning face, and at that point, what is it? That's the relative max for x equals to pi over 6, okay? How about f double prime of 11 pi over 6? In that case, it's the same story, sine 11 pi over 6. This actually becomes negative 1/2. And you get positive 2 radical 3, so it's positive. So that means you have a smiley face, and at the center of the smiley, you have the relative minimum for x equals to 11 pi over 6. Okay, this time we are supposed to use the first derivative test for this function. Let's find the derivative. Y prime is 30x to the 4th minus 120x squared plus 0. Okay, and we can factor this. X squared can be factored out. 30x squared minus 120. I guess we can factor the 30 out also. So if I factor the 30, I get x squared minus 4. And this is 0 when x is equal to 0, and this is 0 when you have x equals to plus or minus 2. Okay. Now, so these are critical numbers. So that's the answer to part A. Now for to do part B, you have to put these critical numbers on the number line, -2, 0, and 2. And now we're going to pick test points. We plug that into this function here, -3 plugged in, that's positive, positive, okay, y prime. If I plug in -1, that's negative. Well, this is always positive because 30 is positive and x squared is always positive. So we only need to figure out what happens here. So that's negative. If I plug in 1 squared minus 4, that's -3, which is negative. If I plug in 3 squared is 9, 9 minus 4 is 5. Okay. So using this, we see that y is increasing and then decreasing and then decreasing and then increasing again. Oh, this is positive. Okay. So we know that this is relative max. So -2 is relative max, and 2 is relative min, and 0 is just it's decreasing and then decreasing again, so this is neither. Okay, now let's think about the graph where it's concave up or down. Concavity has to do with the second derivative, so let's take this and differentiate again. Y second derivative, 4 comes down, 120x cubed minus 2 times 120, that's 240x. We can factor 120x out and you get x squared minus 2. So we know that the concavity has to do with 0 and radical 2 and negative radical 2. Okay. Now if you put test values, this is rather straightforward. So let's just say we plug in -1 and 1 and 2 here and -2. If we use those values, if I plug in 1 for example, it's going to be negative, and all the signs will, you can check that this is positive here and this is positive here and then negative here. So all these are inflection points. So that's the answer to part D. To give you the answer part C, concave up means second derivative is positive, so it's between here and after here. So the answer for part C is the interval negative radical 2 to 0 union radical 2 to infinity. Find the points of inflection and open intervals where the graph is concave up or down. Okay. Now, for this first question, you have to be careful because log doesn't accept all values. The domain for the log is only positive values. So when you're doing A, you're only going to think about the case when x is positive. Okay. Let's differentiate. 4x differentiates to 4. This requires a chain rule. Log differentiates to 1 over, so it's 1 over 2x. And if you differentiate 2x, you get 2. So you end up with 4 minus 2 and 2 cancel, so you get that. Or you can write it as 4x minus 1, sorry. 4x minus 1 over x. Now, when is it not defined? When x is 0, but that's outside our domain, so that we don't count. 4x minus 1 is equal to 0 gives you x equals to 1/4. Okay, so that's the only critical number. Oh, but wait, we're not doing that. We're trying to do concave up and concave down, so we have to do second derivative. Second derivative of this is 4 differentiates to 0, and this differentiates to 1 over x squared. Okay, well, this is x squared, so it's always positive, isn't it? If it's always positive, what does that mean? It's always concave up. So it's concave up on its domain, 0 to infinity. Okay. For part B, let's try to find the first and second derivative. First derivative, you need the product rule. So 8 times e to the negative 3x, I differentiated 8x first, plus 8x times if you differentiate e to the negative 3x, it requires the chain rule, e to the negative 3x times negative 3. So you end up with 8 minus 24x times e to the negative 3x. Okay, it's good to multiply it and factor e to the negative 3x, because that way it's easier to differentiate. Now let's differentiate twice. We need the concavity here. And using the product rule again, it's negative 24 e to the negative 3x, and then 8 minus 24x e to the negative 3x negative 3. So that gives you negative 48 and plus 72x e to the negative 3x. And we see that this is 0 when you have 2/3. Okay, 2/3. So x equals to 2/3 is the point when this is equal to 0. Exponential functions are never 0. Okay. If I plug in 1 into this function, negative 48 plus 72, that's positive. So at 1 it's positive. If I plug in 0, it's negative. So 2/3 is an inflection. Okay. It also requires the inflection point. So here, because it's always concave up, there's no inflection in this case. But in this question B, at 2/3 you have an inflection point. So for part B, the answer is concave down on negative infinity until 2/3, concave up from 2/3 and afterwards because of the sign of f double prime, and then if x is 2/3, y is 16 over 3 e to the 2/3 negative 2. This is the inflection point. Inflection point. Okay, sketch the graph of any function that satisfies the following conditions. So there are 3 inflection points, negative 6, 2, and 5. There are 2 horizontal asymptotes, one of them which is in the x-axis. All right, and fx is differentiable anywhere. Okay. So first, for these questions, you just have to do trial and error. It's hard to draw everything in at once. So f of 0 is 2. Let's say this is 2. F of negative 4 is 0, so it's negative 4 here. F of 2 is 0. So we need a graph that passes through these 3 points. Now f of negative 1 is equal to 0. And then f of 4, this is 2, 4. F of 4 is also, these are the points where you have horizontal tangent lines. So I guess the way you could have a horizontal tangent line is when you have like this, and you have a horizontal tangent line like that. Or another way would be like going like that. But if you do that, then you have to do another sharp turn to go back to 2. So you will have another horizontal tangent here. So I guess this is the correct one. So let's make this part. And then from here to there, it just goes down, and then you have horizontal tangent here. Okay, so that much I think satisfies A and B. Now there are 3 inflection points, negative 6, 2, and 5. So here already it's kind of nice. We already have an inflection point. This is concave down, concave up. So 2 is an inflection point. That's good. And at 5, there should be an inflection point. So I guess it's like that, and then going like that. Okay. And then at -6, you also have an inflection point. So it's going like this, but then at -6 it does that. Okay. And then finally we need two horizontal asymptotes, one of them which is the x-axis. Well, I mean, this side, to have two horizontal asymptotes, that means you need the right side to converge to a single line, on the left side to converge to a single line. That's how you can get two horizontal asymptotes. But since this is closer to the x-axis, I guess this one has to be the one that's getting closer and closer to the x-axis. So let's erase that part and then make it bend like this, and then do a dotted line here so that it gets closer and closer to this, and this other side should be getting closer and closer to some other horizontal asymptote. Now part E says it's differentiable everywhere, and I think this is smooth. I can make it smooth, and that should satisfy everything.